Everything you believe about what makes a planet a home is built on a foundation of profound loneliness. You were raised under the comforting illusion of solitude, the belief in a single, benevolent star commanding a predictable and orderly system. You learned of a sun that rises in the east and sets in the west, a celestial clockwork of magnificent but simple reliability. This daily rhythm is etched into our biology, into our myths, into the very architecture of our civilizations. It is the unchallenged truth of our existence, the first and most fundamental law of our sky. But out there in the silent, sprawling darkness between the worlds, the universe whispers a different, more chaotic truth. It tells us that our stability is not the rule, but a fragile and perhaps vanishingly rare exception. It reveals that the placid solitude of our solar system is a cosmic anomaly, a quiet celestial backwater in a galaxy teeming with violent, complex and astonishing families of stars. We're only now beginning to listen to these whispers, deciphering the faint signals of light from worlds impossibly far away. For centuries our telescopes showed us only single points of light, and we assumed they were just like our own sun's solitary beacons in the night. Yet as our vision sharpened, those single points began to resolve into two, revealing a universe dominated by pairs. Binary stars locked in an intimate and eternal gravitational waltz are the galactic standard. More than half the stars you see in the night sky are not alone. They are partners weaving intricate orbital patterns, exchanging streams of stellar fire, and living out their lives in a dynamic shared dance. The idea of a planet navigating such a system once seemed like pure fantasy, a mathematical impossibility. A world caught between the gravitational tides of two suns was thought to be doomed, destined to be either consumed by one of its stellar parents or flung violently into the desolate cold of interstellar space. It was a place where no stable orbit could ever take root and therefore no life. But the universe, it seems, has far more imagination than we do. We found them. Planets that trace stable looping paths around both stars in a binary pair, witnessing a double sunrise that would sear the imagination. These are the circumbinary worlds born into the heart of a gravitational whirlwind, yet somehow finding a path to endure. We have also discovered planets that cling closely to one star while its distant companion hangs in the sky like a colossal brilliant moon, a second sun in all but name. These discoveries shattered our provincial view of how planetary systems must be arranged. They demonstrated that nature's capacity for creation far exceeds our limited earthbound expectations. The discovery of these two sun worlds forced us to redraw the maps of the cosmos, to reconsider the very definition of habitable. It was a revelation that moved us from a simple geocentric model to a more complex and wondrous reality. Yet even this profound paradigm shift was only the beginning. It was merely the first step away from the comfortable solitude of our own planetary home, a gentle introduction to a reality more intricate and more alien than we could ever have conceived. Because if two suns are possible, a terrifying and exhilarating question naturally follows a question that pushes the boundaries of physics and imagination to their absolute breaking point. What about three? What happens when the elegant waltz of a binary system is invaded by a third disruptive partner? The calm, predictable mathematics that can with effort describe the dance of two bodies completely collapses. Introducing a third body creates a problem of such notorious complexity that it has vexed mathematicians and physicists for centuries. It is the genesis of chaos. Not chaos in the colloquial sense of simple messiness, but in the profound mathematical sense a system so sensitive to initial conditions that its future becomes fundamentally unpredictable. A system of three stars is not a waltz, it is a mosh pit. A swirling, intricate and often violent gravitational knot where orbits are not clean ellipses but wild looping spirographs of breathtaking complexity. The stars themselves are in constant motion relative to one another, pulling and twisting space-time in a relentless shifting contest of gravitational supremacy. For a planet to be born into such a cataclysmic environment seems beyond all reckoning. Its nascent protoplanetary disk, the spinning cloud of gas and dust from which worlds are made, should be torn to shreds by the competing gravitational forces before it could ever coalesce. The tidal stresses would be unimaginable, kneading and shearing the raw material of creation into useless scattered debris. Any planetary embryo that did manage to form would face a harrowing existence. It would be a cosmic pinball ricocheted between the gravitational fields of its three stellar masters. Its orbit would be a tightrope walk over an abyss of annihilation, where the slightest deviation could lead to a fiery plunge into one of the suns or an ignominious ejection into the void. To us conditioned by the gentle clockwork of our own solar system, a planet in such a place feels like a violation of natural law. It is a world that by all rights simply should not exist. And that is precisely why the thought of it is so intoxicating. It represents the ultimate challenge to our understanding of the cosmos. So let us dare to imagine it. Stand with us just for a moment on the surface of this impossible world. The ground beneath your feet is solid, but the sky above is a canvas of perpetual rolling transformation. There is no single dawn, but a cascade of them. The first sun, a brilliant blue-white giant, crests the horizon, flooding the alien landscape with a sharp analytical light. It casts a short, dark, and perfectly defined shadow behind you. Hours later, as this first sun climbs towards its zenith, a second star appears. This one is smaller, a fiery orange dwarf, and its light is warm, the colour of molten honey. As it rises, a second shadow is born paler and softer than the first, stretching out in a different direction. You now cast two shadows, a ghostly echo of yourself painted upon the ochre dust. The two suns move across the sky at different speeds, their light mingling to create an ethereal, ever-changing palette on the clouds above. The very concept of midday becomes meaningless here. There is only a slow celestial symphony of light, a continuous ebb and flow as the luminaries trace their complex interwoven paths across the celestial sphere. Then, as the first two suns begin their descent, the third and most distant star makes its grand entrance. It might be a faint crimson ember, a red dwarf hanging in the sky like a blood-orange jewel. Its light is ancient and tired, casting a third impossibly long and ghostly shadow that merges with the other two, creating a complex shifting pattern at your feet. Imagine the sunset. It is not a singular event, but a prolonged three-act drama. The blue giant sinks first, its departure plunging the world into a sudden cool twilight. Then the orange dwarf follows, setting fire to the horizon from a different point, its lingering glow painting the underside of the clouds in shades of apricot and rose. For a brief magical period, the world is bathed in the gentle ruddy twilight of the red dwarf alone. This is the closest you will ever come to night, a deep crimson dusk where the stars of the wider galaxy finally burn through the overwhelming glare. But this reprieve is fleeting. Soon the blue giant will rise again from a new point on the horizon, beginning the cycle anew. On this world, the sky is never truly dark. It is a kaleidoscope of overlapping days, a place of triple dawns and triple dusks, a world without the comforting blanket of true night. What would it be like to live under such a sky? How would life, if it could possibly arise in such a turbulent system, adapt to this eternal shifting twilight? Would plants evolve 3 different kinds of chlorophyll to capture the light from 3 different stellar spectra? Would creatures have eyes that could cope with the constant dramatic shifts in light intensity and colour? Would their circadian rhythms be tied not to a simple 24-hour cycle, but to the great overarching cycle of the stars themselves, a great year that might last for centuries as the 3 suns complete one full chaotic period of their dance? The psychological impact would be just as profound. We as humans find poetry in a singular sunrise, comfort in the reliable passage of a day. Our sense of time, of beginning and end, is tied to this rhythm. To exist on a world with no clear beginning or end to its day would be to live in a state of perpetual temporal ambiguity. It would be a world that erases the very concepts of yesterday, today, and tomorrow, replacing them with a fluid, unending present illuminated by a celestial triumvirate. This is not a flight of fancy. This is not science fiction. This is the frontier of modern astronomy, because we have found these systems. In the constellation of Orion, nearly 350 light-years from Earth, lies a stellar nursery known as GW Orionis. There astronomers have found not just a triple star system, but a vast warped and broken disk of dust and gas circling all 3 stars, the raw material for planets. It is a protoplanetary disk torn into distinct misaligned rings, a cosmic gyroscope knocked off kilter by the gravitational chaos at its centre. Within these rings, the seeds of new worlds may be forming right now, gestating in the heart of a gravitational storm. And elsewhere in systems like LTT 1445a, we have found a confirmed planet, a terrestrial world orbiting one star in a triple system, constantly bathed in the light of its two stellar companions. These are not theoretical constructs. They are real places. They are destinations our telescopes can visit, and their existence presents us with the most tantalizing puzzle in planetary science. The very presence of these worlds breaks our models of planetary formation. The classic neat and tidy story of a single spinning disk of dust slowly giving birth to planets in orderly circular orbits simply does not work here. The raw gravitational power of three stars should have prevented their birth, and their continued existence should be impossible. And yet they are there. Their survival is a testament to nature's relentless drive to create, to form worlds, even in the most hostile and violent corners of the galaxy. They force us to ask the most fundamental questions. How? How in the primordial chaos of a triple star birth does enough material gather to form a planet? Does it form far away and migrate inwards, undertaking a perilous journey through a gravitational minefield? Is it a captured rogue planet, a wanderer from another system ensnared by the triple star's immense gravity? Or does nature have a method for world building that we have yet to even dream of? A mechanism that thrives in chaos rather than shying away from it? These are the questions that drive us forward, that push us to build bigger telescopes and design more sophisticated simulations. Each of these impossible worlds is a clue, a single, luminous data point in a grand cosmic mystery. They are cosmic outliers that challenge our most cherished theories, and in doing so promise to reveal a deeper and more universal truth about how planets are born across the galaxy. They remind us with humbling authority that our own home is just one possible outcome in a universe of infinite variety. The story of a planet with three suns is more than just an astronomical curiosity. It is a story about our own place in the cosmos. It is a narrative that decenters our experience and forces us to confront the staggering diversity of worlds the universe has to offer. It is a journey into the heart of celestial chaos, a quest to understand how stability can emerge from violence, and how a world against all odds can find a way to endure. To find the answers, to truly comprehend the miracle of such a planet's existence, we cannot start on its surface. We must journey back to the very beginning. We must travel to the violent, swirling heart of a stellar nebula, to the primordial clouds of gas and dust where stars and the impossible triumphant worlds that orbit them are born. There is a rhythm etched into the very core of your being. A biological clock wound by the patient, predictable rising and setting of a single magnificent star. For countless generations, this was the unquestioned truth, the primordial metronome of life itself. Day followed night. One sun reigned in the heavens. This simple, profound experience shaped our gods and our myths, our poetry and our science. It became the bedrock assumption upon which we built our model of the cosmos. We saw our sun, our soul, not as one possibility among many, but as the universal standard, the archetype of a star. Every other pinprick of light in the night sky we believed must be just like it, a solitary monarch ruling its own distant court of planets, each one a silent, lonely kingdom unto itself. This wasn't arrogance, it was an extrapolation from the only data we had. The data of our own senses, of our own profound, singular dawn. But what if that fundamental rhythm, that celestial solitude, wasn't the rule but the exception? What if the universe was vastly more creative, more chaotic and more crowded than our imaginations could possibly allow? The first crack in this monolithic worldview was not a thunderous cataclysm but a quiet revelation whispered through the lens of a telescope. It came from the patient work of astronomers like William Herschel, in the late 18th century, men who were not just cataloguing the stars but truly observing them night after painstaking night, year after patient year. They were tracking their subtle movements against the vast static backdrop of the heavens, and in doing so they stumbled upon something utterly bewildering. Certain stars which to the naked eye appeared as single points of light resolved through their polished glass into two. Not just two stars that happened to be near each other in the sky, an optical illusion of perspective across unfathomable distances. No, these were true companions. They were locked in an intimate and eternal gravitational embrace, a celestial dance that defied the simple logic of a solitary sun. This was the discovery of the binary star. And it was a moment of profound scientific shock. Imagine the intellectual whiplash. For all of history, we believed a star was a singular entity. Suddenly, the universe was showing us that stars could come in pairs orbiting a common centre of gravity like cosmic dance partners. Systems like Castor in the constellation Gemini or Mizar in the Big Dipper's handle revealed themselves not as lonely beacons, but as dynamic, interconnected families of light. This discovery was more than just a novelty. It was a fundamental challenge. It forced us to reconsider the very nature of gravity itself. We had to accept that the same force that anchors you to the Earth, the same force that shepherds our planet on its yearly journey, was capable of orchestrating this far more complex and beautiful choreography. It meant that a sky could have two suns. The mind reeled at the possibilities. What would a sunset look like on a planet in such a system? Would there be two shadows? Would night ever truly fall? These were questions of poetry, of imagination. But for scientists, the discovery of binary stars opened a Pandora's box of far more troubling questions, questions of mathematics and stability. If two stars could dance together, could three, could four? And most importantly, could a small fragile planet possibly survive in the middle of such a gravitational tug-of-war? The universe, it seemed, was only just beginning to reveal its complexity, and with it the terrifying depths of its potential for chaos. To understand the scale of the problem, we must journey back another century to the mind that first gave us the language to even describe this celestial dance, Isaac Newton. With his law of universal gravitation, Newton didn't just explain why an apple falls from a tree. He handed humanity a key, a mathematical Rosetta Stone, to unlock the secrets of the cosmos. His elegant equations described a universe of breathtaking order, a place where the motion of the planets was not the whim of deities, but the predictable result of a fundamental measurable force. This was the birth of celestial mechanics, and for a time it seemed we had solved it all. The so-called two-body problem was a resounding success. Given the mass of two objects, a star and a planet for instance, and their initial positions and velocities, Newton's laws could predict their exact paths for all of eternity. Their orbits would be perfect, repeating ellipses, a clockwork of divine precision. The solar system, once a source of mystery and dread, was transformed into a grand predictable machine. We could forecast eclipses to the second chart, the return of comets to the decade. There was a profound comfort in this newfound order. The universe, it appeared, was rational, it followed rules, and we, with the power of mathematics, could understand them. The discovery of binary stars fit neatly into this framework. A two-star system was just another expression of the two-body problem. The dance was more complex than that of a planet and a star, but it was still a dance for two governed by the same elegant, solvable equations. It reinforced our confidence, our belief that we were finally grasping the fundamental blueprint of creation. We had found the master equation for the heavens, but this triumph, this beautiful, orderly vision of the cosmos was built upon a fragile foundation. It worked perfectly for two bodies. The moment you introduce a third, the entire magnificent structure of Newtonian certainty comes crashing down into a terrifying abyss of chaos. This is the infamous n-body problem, and for our purposes, the three-body problem. And it stands as one of the most vexing and profound challenges in the history of physics and mathematics. On the surface, it seems deceptively simple. If you can calculate the gravitational interactions between two bodies, why not just add a third set of calculations for the new object? But the universe is not so simple. In a two-body system, the planet orbits the star's centre of mass in a clean, predictable ellipse. When you add a third body, another star, everything changes. Star A pulls on star B pulls on star A, but now star C is pulling on both A and B are pulling back on C. But wait. As star C pulls on star A, it changes star A's position. This tiny change in star A's position instantaneously alters its gravitational pull on star B, which in turn alters star B's pull on star C, which alters star C's pull on star A. You have entered a maddening infinite feedback loop. Every object is constantly changing the gravitational field for every other object. It's not a simple dance anymore. It is a chaotic melee, a gravitational free-for-all, where every participant's next move is dependent on the simultaneous moves of everyone else. The beautiful repeating ellipses of the two-body problem dissolve into a tangled mess of wildly unpredictable, non-repeating trajectories. The system becomes a cosmic game of billiards, played on a warped table where the balls themselves are massive magnets, constantly twisting the fabric of the game as they move. The great French mathematician Henri Poincaré at the end of Fry was the first to truly confront this mathematical monster. He was searching for that same Newtonian perfection, a stable general solution to the three-body problem. He wanted to find the master equation for three stars. He never found it. Instead, what he discovered was far more unsettling. He found that no such general solution exists. The system is in its very essence deterministic but not predictable. We know the rules, the laws of gravity are simple, but applying them in this context leads to a complexity that mushrooms into infinity. A minuscule change in the starting position of one of the stars, a difference so small it would be impossible to even measure, could lead to a drastically, wildly different outcome millions of years down the line. One star might be ejected from the system entirely. Two might merge in a fiery apocalypse. The three might settle into a bizarre temporary pattern before flying apart. There was no way to know for sure. Poincaré had stared into the heart of mathematical chaos. The divine clockwork of Newton was not broken, but it was revealed to be a special case, a quiet, orderly corner in a much wilder, untamed cosmos. The promise of perfect prediction was an illusion. And with this realization, the dream of a planet orbiting three suns began its descent from the realm of imagination into the category of physical impossibility. Now take this maelstrom of gravitational violence, this mathematical pandemonium, and introduce a fourth, much smaller object. A planet. A tiny, fragile world caught between the competing tyrannical pulls of three massive warring suns. To the physicists and astronomers of the 20th century, the thought was absurd. It was a recipe for cosmic annihilation. They ran the numbers, they built the first crude computer simulations. And the results were always the same, utter and complete devastation. The planet in such a system wouldn't have an orbit. It would have a death sentence. It would be a gravitational plaything for the stars. Imagine that world. It would be violently whiplashed from one trajectory to another. In one scenario, its path might be warped into a collision course with one of its stellar overlords to be swallowed whole in a final fiery plunge. In another, a close gravitational encounter with one star could act as a colossal slingshot, ejecting the planet from the system, entirely condemning it to an eternity of frozen exile as a rogue world drifting alone in the blackness between the stars. Perhaps the most brutal fate would be to be passed back and forth between the stars, its orbits stretched and squeezed, triggering catastrophic geological upheaval, its very crust torn apart by tidal forces. The delicate, stable ellipse that gives Earth its predictable seasons would be replaced by a path of pure chaos. There would be no predictable year, no reliable cycle of warmth and cold. One moment the planet might be perilously close to a celestial blowtorch, its atmosphere boiled away, its oceans turned to steam. The next, it could be flung far out into the frozen abyss, its surface encased in ice before being yanked back toward the inferno. This wasn't a stable home for life. It wasn't even a stable home for a rock. The scientific consensus was clear, and it was nearly unanimous. Stable long-term planetary orbits in a triple-star system were not just unlikely. They were a violation of the fundamental principles of orbital mechanics. The intricate gravitational dance of three suns left no room for a partner as small and vulnerable as a planet. The system would chew it up and spit it out. For decades, this conclusion stood as a formidable wall of mathematical certainty. The search for exoplanets, when it began in earnest, focused on stars like our own, the quiet, solitary ones. Looking for a world around three suns was considered a fool's errand, a waste of precious telescope time, a journey into a realm that mathematics had already told us was barren. The idea was relegated to the pages of science fiction, a fantastical setting for impossible stories but not a serious target for scientific inquiry. The universe was chaotic, yes, but there were still rules. And the rules, as far as we could understand them, were absolute. 3 stars, no planets. The case was closed. And yet the cosmos has a recurring habit of being more inventive than its observers. Our mathematical models, however powerful, are only an approximation of reality. Our skepticism, however well-founded, can sometimes be a form of blindness. While the grand equations of chaos decreed such worlds impossible, out in the silent darkness, hundreds of light-years away, a strange and persistent signal was beginning its long journey toward our telescopes. It was a whisper of light, a subtle dimming a message that would ultimately force us to question everything we thought we knew about the delicate dance of gravity and the birth of worlds. The universe, it seemed, had a secret it was finally ready to share. But even with our eyes fixed on that bewildering stellar triad, a chasm of ignorance lay between our questions and any possible answer. Before we could contemplate the physics of a world with 3 suns, we had to confront a far more elementary and for centuries a far more humbling uncertainty. Could we find any planets at all beyond the familiar confines of our own solar family? For most of human history, the answer was a silent, resounding no. The challenge was almost insulting in its simplicity and scale. A planet, even a giant like our Jupiter, is a cosmic speck of dust next to its parent star. It shines with no light of its own, a mere mote lost in the cataclysmic glare of a thermonuclear furnace millions of times brighter. Searching for one was like trying to spot a single unlit firefly hovering beside a military searchlight from 100 miles away. The task seemed not just difficult but fundamentally impossible, a barrier erected by the very laws of physics. The universe, it seemed, was content to keep its secrets. To break this impasse, we couldn't just build a better telescope. We had to learn to see the universe in an entirely new way. We had to learn to look not for the planet itself, but for its ghost. For the subtle, rhythmic signature its gravity would imprint upon its star. This first revolutionary technique, known as the radial velocity method, was an act of supreme scientific cleverness. It wagered that even a colossal star is not a perfect immovable anchor. A planet in its endless gravitational embrace doesn't simply orbit its star, they orbit each other, dancing around a common centre of mass. For a massive star and a tiny planet, that centre is deep inside the star itself, but it's not precisely at its core. This means the star doesn't sit still. It performs an infinitesimal wobble, a tiny repeating pirouette in space pulled to and fro by its unseen planetary companion. The genius was in realizing we could detect this stellar shudder from light years away. As the star wobbles slightly towards us in its cosmic dance, its light waves are compressed, shifting towards the blue end of the spectrum. As it wobbles away, the light waves are stretched, shifting towards the red. It is a celestial heartbeat, impossibly faint, a rhythmic pulse of colour betraying the presence of a hidden world. For years, astronomers chased these spectral ghosts, pushing their instruments to the very edge of sensitivity. Then, in 1995, the signal came through. A Swiss team detected a frantic, powerful wobble from the star 51 Pegasi, a sun-like star 50 light-years from Earth. The data was unambiguous, but it was also utterly bizarre. The ghost it revealed was a monstrous, a gas giant half the mass of Jupiter. Yet this colossal world wasn't orbiting in the frigid outer darkness where our theories predicted it should be. It was practically skimming the surface of its star, completing an entire orbit, an entire year in just 4 Earth days. It was a hot Jupiter, a class of planet that no one had believed could exist, roasted by stellar radiation to temperatures that would vaporize iron. The discovery of 51 Pegasi b was not just a confirmation, it was a revolution. It was the first note in a symphony that would change everything. It proved that worlds beyond our own were not just a philosophical dream, but a detectable reality. More importantly, it served as a stark, humbling warning. The universe was under no obligation to conform to our tidy Earth-centric models of how a solar system should be built. The floodgates were open. While the wobble method had proven planets were out there, it gave us only a shadow sense of their true nature, revealing mass and orbit, but little else. A second, even more powerful technique was needed to truly begin a galactic census. This was the transit method, an idea as elegant as it was simple. If a planet's orbit happens to be perfectly aligned with our line of sight, Then once per revolution, it will pass directly in front of its star. From our vantage point, this passage, this transitua, would cause a minuscule temporary dip in the star's brightness. It would be a fleeting shadow play on a cosmic scale, the equivalent of a single fruit fly, passing in front of a distant lighthouse beam. The dimming is almost imperceptible, often less than 1/100th of 1%. Detecting it required a new kind of observatory, one with a patient, unblinking gaze designed to stare relentlessly at a single patch of sky for years on end, measuring the light from hundreds of thousands of stars with unprecedented precision. That observatory was Kepler. Launched in 2009, the Kepler Space Telescope was more than an instrument. It was a hunter, humanity's first dedicated planetary census taker. For 4 years, Kepler stared, and the universe began to give up its dead. The data that streamed back to Earth was a revelation, a deluge of worlds that exceeded even the most optimistic predictions. It found small, rocky planets. It found colossal gas giants. It found super-Earths and mini-Neptunes. Strange new categories of worlds that have no analogue in our own solar system. It found planets orbiting so close to their stars their surfaces were likely molten oceans of lava. It found others so far out they were encased in eternal ice. The trickle of discoveries turned into a torrent. The question was no longer if other planets existed, but how many billions of them populated our galaxy alone. We had entered a new epoch of astronomy. The cosmos, once perceived as a vast and sterile emptiness, punctuated by lonely stars, was being repopulated before our very eyes. It was revealed to be a celestial wilderness teeming with an astonishing diversity of worlds. Kepler's legacy was to transform planets from rare exceptions into the common expected outcome of star formation. They were everywhere, and it was within this treasure trove of new worlds that astronomers began to ask a more daring question. The vast majority of stars in the Milky Way are not solitary suns like our own. Over half of them, perhaps more, live in binary, or even multiple star systems locked in complex gravitational ballets. For decades, these systems were written off as planetary graveyards. The gravitational dynamics were thought to be simply too violent, too chaotic for planets to ever form, let alone survive. Any nascent disk of dust and gas, the raw material for planet building, would surely be torn to shreds by the competing gravitational tides of 2 stars. Any fledgling planetesimal that managed to coalesce would be unceremoniously ejected into the freezing abyss of interstellar space, a cosmic orphan flung from its violent home. But science fiction had long dared to imagine otherwise. A generation had grown up mesmerized by the iconic image of a young farm boy on the desert planet, Tatooine gazing out at the horizon as 2 suns dipped below it. Could such a world, a circumbinary planet, actually exist? Was it pure fantasy, or did the universe possess an imagination as bold as our own? Armed with the powerful transit and radial velocity techniques, astronomers turned their attention to these turbulent systems. The hunt was exponentially more difficult. For the transit method, you were no longer looking for a simple periodic dimming of a single steady light source. You were looking for a faint dip in the combined fluctuating light of 2 stars that were themselves eclipsing each other as they orbited. The signal was buried in a storm of noise, a complex light curve of dips and swells that had to be meticulously modelled and subtracted before the impossibly subtle signature of a transiting planet could be teased out. It was a Herculean task of data analysis. Yet in 2011, the Kepler team announced a breakthrough that sent shockwaves through the scientific community and thrilled dreamers around the world. They had found it. Orbiting the binary star system Kepler-16, 200 light-years away, was a Saturn-sized gas giant. They had found the first definitive real-life Tatooine. Watching the light curves from this system was like seeing a prophecy fulfilled. You could see the primary dip as the smaller star was eclipsed by the larger the secondary dip, as it passed behind, and then a third, fainter and irregular set of dips. These were the transits of the planet, sometimes crossing one star, sometimes the other, its passage a testament to a world with 2 suns. The discovery of Kepler-16b and the many circumbinary planets that followed proved that nature could indeed find a way. But this triumph only deepened the mystery of their creation. The old elegant model of planetary formation, a slow, patient process of dust grains sticking together in a calm, orderly protoplanetary disk completely falls apart in the gravitational blender of a binary star system. The violent tidal forces should have prevented any of the foundational building blocks from ever clumping together in the first place. It was a paradox. The planets were undeniably there, yet our best theories insisted they should never have been born. This crisis forced astrophysicists back to the drawing board, sparking a wave of new, more creative and more violent theories. Perhaps these planets did not form where we see them today. Maybe they were born in a much wider, more stable orbit, far from the gravitational chaos of their twin suns, and then slowly migrated inward over millions of years. Or perhaps formation happened in a very specific narrow ring of stability, within the disk a calm harbour, where gravity found a temporary delicate balance, allowing worlds to coalesce in a frantic burst before the system's dynamics changed. The existence of these Tatooine worlds transformed them from science fiction curiosities into crucial test cases, cosmic laboratories that are forcing us to rewrite the very first chapter in the story of how planets come to be. Simultaneously, these discoveries were forcing a radical re-evaluation of one of the most cherished concepts in our search for life, the habitable zone. For a single star like our Sun, the idea is straightforward: a Goldilocks ring of orbits not too hot and not too cold, where liquid water could potentially exist on a rocky planet's surface. But what does a habitable zone even look like when you have two suns? The answer is a far more complex and dynamic reality. The zone is no longer a simple static ring. Instead, it becomes a fluid, shifting three-dimensional space that morphs and warps as the two stars orbit each other. A planet in such a system wouldn't experience simple, predictable seasons. Its climate would be governed by a complex interplay of orbital mechanics. Imagine a world orbiting two stars of different colours and temperatures, a hot blue-white star and a cooler orange dwarf. At one point in its year, the planet might be bathed in the intense radiation of the hotter star, while at another it could swing closer to the cooler one, or receive the blended light of both. The habitable zone would pulse expanding and contracting breathing with the rhythm of the binary star's own dance. A planet might spend part of its orbit in a life-giving temperate zone only to be plunged into a deep freeze or a scorching heatwave as it continues on its path. This redefines habitability not just as a matter of place, but of timing of surviving a climate that could be brutally inconsistent over eons. But even this mind-bending complexity was proving to be just a stepping stone. As astronomers grew more confident in their ability to untangle the light of two suns, they began to push their techniques even further. They started looking at the true gravitational outlier systems, where the dance was not a simple waltz for two, but a chaotic melee for three. We had proven that a planet could survive the gravitational pull of two stars. The impossible had been made real. We had found worlds that defied our theories of formation and redefined our concept of a stable home. And with each new discovery, with each circumbinary world added to our celestial catalogue, the confidence of the scientific community grew. We had built the tools, we had honed the techniques, we had learned to read the subtle language of starlight to find the whispers of hidden worlds in the overwhelming roar of their suns. The success in binary systems didn't just add to our knowledge, it emboldened us. It gave us permission to ask an even more audacious, more seemingly ludicrous question. If gravity could find a way to permit a world to dance with two stars carving out a pocket of stability amidst the chaos, what happens when you add a third? Does the delicate dance continue finding an even more intricate and beautiful solution? Or does the entire system finally descend into absolute world-shattering and inescapable pandemonium? For decades, the hunt for these impossible worlds yielded only silence. Our models predicted chaos, our equations screamed instability, and the cosmos itself seemed to concur, offering no evidence that a planet could survive the gravitational turmoil of a triple-star system. The question lingered in the quiet halls of astronomy, a tantalizing ghost, a theoretical dream awaiting its physical incarnation. Then in 2016, from a remote peak in Chile's Atacama Desert, that long silence was shattered. The message arrived not as a whisper but as a faint solitary photon, a single particle of light that had travelled for 340 years from the direction of the constellation Centaurus. It was a messenger from a place our science had deemed a wasteland, carrying with it a revelation that would forever alter our celestial map. This was not another computer simulation or a hopeful mathematical model. This was a discovery etched in the language of light itself. The astronomers who received this message were wielding one of humanity's most powerful eyes on the universe, the Very Large Telescope. More specifically, they were using an instrument attached to it, a masterpiece of optical engineering called SPHERE. Its name stands for Spectropolarimetric High Contrast Exoplanet Research, but you can think of it as the ultimate stellar ghost hunter. Its singular purpose is to achieve the near impossible to directly image a planet orbiting another star. You have to understand the staggering scale of this challenge. Imagine trying to photograph a single firefly hovering right beside the brilliant blinding face of a military searchlight. Now imagine that searchlight is hundreds of light years away. The sheer glare of the parent star, a billion times brighter than the planet, overwhelms and erases any trace of the world we seek. It's a problem of contrast so extreme it has stymied observers for a century. SPHERE, however, is designed to cheat this fundamental law of physics. It begins its work before light even enters the instrument, using a technology that sounds like science fiction adaptive optics. As starlight streams down through our turbulent atmosphere, it gets distorted and blurred, causing stars to twinkle. This twinkling, so beloved by poets, is the mortal enemy of the planet hunter. SPHERE combats this with a deformable mirror, a thin, flexible surface that is adjusted by over 1,000 tiny actuators, 1,000 times per second. It is a hyper-speed robotic dance precisely calculated by a supercomputer to cancel out the atmospheric distortion in real time. The result is an image of a star that is unnervingly sharp, as if our atmosphere had been momentarily peeled away, granting us a crystal-clear window into the depths of space. But even with a perfect stellar image, the glare remains. This is where SPHERE's second trick comes into play, a coronagraph. Named after the instruments used to study the sun's corona, it is in essence an incredibly sophisticated mask and artificial eclipse. A tiny precision-engineered metal disc is placed directly in the path of the starlight, blocking the brilliant furnace of the star itself and allowing the far fainter light from its immediate vicinity to shine through. It's a delicate, high-stakes game of celestial hide-and-seek. The team led by a young doctoral student named Kevin Wagner was not looking for a planet in a triple system. They were conducting a survey of young hot stars, hoping to catch planets in the very act of their formation. The target was a star designated HD 13939, a luminous, massive body that serves as the gravitational anchor for its two smaller companions. For years, astronomers knew this star was not alone. They knew of its partners, a tightly knit pair of smaller stars swinging around each other in a fiery, intimate waltz. The system was already a marvel of cosmic architecture, but no one, not even in their most optimistic projections, expected to find a planet swimming in these treacherous gravitational waters. As the adaptive optics settled and the coronagraph slid into place, the blinding light of the primary star HD 13939A was suppressed. The digital sensor began its long exposure, patiently collecting the ancient photons that had completed their interstellar journey. And then slowly, pixel by pixel, it emerged. A single faint point of light, a whisper in the cosmic dark. It was precisely where no world had any right to be. Finding a dot of light near a star is by itself not a discovery. The universe is littered with them. The crucial question, the one that separates a breakthrough from a false alarm, is whether that dot is truly a companion or merely a distant, unrelated star that happens to lie along the same line of sight. Is it a member of the family or a photo-bombing stranger from across the galaxy? To answer this, astronomers rely on a beautifully simple principle, known as common proper motion. Everything in our galaxy is moving. Stars are not fixed points. They drift through space, pulled by the galaxy's rotation, each on its own grand orbital path. If the newfound object was a distant background star, then, as the HD 1393999 system moved across our sky over months and years, the two would appear to drift apart. The planet candidate would be left behind a stationary beacon as its supposed parent stars journeyed onward. But if it was a true planet, a gravitationally bound world, it would move with them. It would be locked in step, a loyal partner in their galactic voyage. So began the painstaking process of confirmation. The team had to comb through archival data from previous years, searching for earlier images of the same patch of sky, looking for any sign of this faint companion. They found it a ghostly presence in older, less refined observations, and as they mapped its position over time, the truth became undeniable. The faint dot was not stationary. It was moving, and it was moving in perfect lockstep with the three suns. It was no stranger. It was family. They had found it. A planet 4 times the mass of Jupiter in a confirmed orbit around 3 stars. They named it HD 131399. The confirmation sent a shockwave through the astronomical community. The ghost had materialized. The myth was made real. And with its reality came a whole new set of bewildering questions, chief among them, how could this possibly work? What kind of path must this world trace to survive such a chaotic dance? As computer models were fed the planet's position and mass, the first glimpses of its extraordinary orbit began to emerge. It was a path unlike anything ever seen in our own solar system. The planet, this gas giant behemoth, orbits the largest central star, the one we call HD 1313A. But its orbit is immense, a vast sweeping ellipse that takes it more than twice the distance that Pluto is from our Sun. Out here, in the cold, distant suburbs of the system, the gravitational grip of its primary star is tenuous, and it is here that the influence of the other 2 suns becomes critical. Those 2 smaller stars, B and C, are themselves locked in a tight orbit, circling each other like a spinning celestial dumbbell. And this entire binary pair, this whirling duo, also orbits the main star A, but at a much greater distance. The planet finds itself caught in the middle of this gravitational tug-of-war. Its journey is a perpetual high-stakes balancing act. For roughly half of its colossal 550-year orbit, the 3 suns would appear relatively close together in its sky. From the planet's perspective during this season, it would seem to be a world with one enormous, brilliant sun flanked by 2 smaller but still dazzlingly bright companions. But as the planet sweeps along its path, it moves towards a point where the central star and the binary pair are on opposite sides of its sky. It is here that the true magic and the true terror of its existence is revealed. The planet is literally pulled between them. Its orbit is not a simple, clean ellipse like Earth's. It is a dynamic, stretching, wobbling path, a celestial tightrope walk. Computer simulations show that its orbit lies at the very razor's edge of stability. If it orbited just a little bit wider, it would be flung out of the system, entirely ejected by the binary pair's gravitational slingshot into the lonely abyss of interstellar space. If it orbited just a little bit closer, its path would eventually decay, sending it spiraling into the fiery embrace of its primary star. It lives against all odds in a narrow, precarious zone of survival, a sliver of gravitational calm in a sea of chaos. This is not just a planet orbiting 3 suns. It is a survivor, a testament to the universe's ability to construct wonders in the most improbable of circumstances. And with the physics understood, we can finally dare to imagine the view. Stand with us now on the swirling cloud tops of this gas giant. Look up at the alien firmament above you. The year here is long, a 5.5-century crawl through a shifting celestial dreamscape. For about 1/4 of that year, a period longer than a human lifetime, the 3 suns are always in the sky. There is no night. One sun sets, but another is already high overhead, and the third is rising. Daylight is perpetual, a constant unyielding bath of tricoloured light. Imagine a searing white-yellow giant, a smaller, cooler yellow companion, and a dim red dwarf, all tracing their own independent arcs across the heavens. What would a sunset look like? It would not be a singular event, but a drawn-out process, a trinity of farewells. The sky would bleed from orange to crimson to deep violet, but the darkness would never fully take hold. Shadows would be a complex, bewildering tapestry. Every object would cast not 1 but 3 distinct shadows, each of different lengths, different sharpness, different colours, all shifting and merging as the suns wheeled overhead. A forest on such a world, if one could exist, would be a disorienting maze of overlapping silhouettes. Then, as the planet continues its epic journey, it enters the other season, the season of the triple sunrise. For another century, the world would experience a more familiar cycle of day and night. But each dawn would be a spectacular triple feature. The 3 suns clustered together in the sky would rise in succession, a cascade of light washing over the planet. One moment a single point of light breaches the horizon, then another and another. The sky would fill with their combined glare, a triad of fire ruling the celestial stage before beginning their slow descent together. This is the sky of HD AB. A sky that defies our simple terrestrial experience. A sky that proves the cosmos has an imagination far more vivid than our own. The discovery was a landmark, a moment where theory finally shook hands with reality. For a time, it was the definitive proof that such systems could exist. It was our poster child for impossible worlds, and this is where the story should have ended. A triumphant discovery, a new chapter in our understanding of the cosmos. But science is rarely that simple. It is a restless, self-correcting process of inquiry, and even its most celebrated discoveries are subject to relentless scrutiny. As other teams of astronomers turned their own powerful telescopes towards this remarkable system, they began to collect new data. More precise measurements of the planet's motion, a clearer picture of the stars themselves. And as the evidence accumulated, a new, far more complex and in many ways more thrilling mystery began to take shape. The beautiful, stable picture we had painted of this impossible world started to fray at the edges. The data was no longer fitting the model. The elegant dance we thought we had finally understood was revealing itself to be something else entirely. The ghost we thought we'd captured and catalogued was proving to be more elusive and more enigmatic than we ever imagined. The universe, it seemed, was not yet finished with its surprises, and so we have found it. A ghost in the machine of the cosmos, a world that should not be confirmed in the faint rhythmic dimming of its 3 parent stars. The mathematical models, once pure theory, now have a home. A point of light, a testament to the universe's boundless imagination. But to know that such a world exists is one thing. To stand upon its surface in our mind's eye, to feel the pull of its impossible sky, that is another endeavour entirely. The discovery was the end of a search, but it is only the beginning of a story. For this planet, now that we know its name, forces us to confront a question far more profound than what if. It demands we ask, what is it like? What happens when a planet is not born to a single nurturing star, but is instead a child of chaos, caught in the eternal gravitational embrace of 3 warring suns? To imagine this world, you must first forget everything you know about a day. You must abandon the simple, comforting cycle of sunrise and sunset, the gentle rhythm that has governed all life on Earth for billions of years. On this world, the sky is a vast, celestial stage for a drama of perpetual motion. There is no single dawn. Instead, there are 3. One star, a fiery yellow giant, might rise in the east, painting the clouds in hues of gold and amber. But as it climbs, it is chased by a pair of smaller, fiercer suns, a tight binary of a brilliant white dwarf and a blood-red giant locked in a blistering orbital dance. They do not follow the same path. Their rise is a dizzying, complex arc, sometimes appearing as a single blinding point of light, other times resolving into 2 distinct malevolent eyes staring down from the heavens. There is no simple noon. At times, all 3 suns might converge in a single quadrant of the sky, a tri-solar conjunction that creates a searing, shadowless blaze. The light is not just bright, it is absolute. It scours the landscape bleaching colour from the very rock, creating a glare so intense it would feel like standing inside the filament of a light bulb. But this peak of intensity is fleeting. The 3 suns are in constant relative motion, their paths weaving a celestial braid across the firmament. A moment of tri-solar noon might be followed by an afternoon where the suns drift to opposing horizons, stretching the light, creating a world of impossible shadows. Imagine standing in a field of alien rock. Your own shadow would not be a single loyal companion. It would be a trio of spectral forms, each cast by a different sun, each of a different length, a different sharpness. One a deep and defined silhouette from the closest star, the others fainter, more ethereal spectres stretching and contorting as their parent stars move. The world is a place of overlapping twilights, of perpetual shifting dawn. True night, the profound star-dusted darkness we know, is an almost mythical event on this planet. It can only occur during the brief precious alignment when the world's orbital path carries it to a position where all three suns are simultaneously below the horizon. For most of its long, languorous year, some part of the planet is always illuminated. An evening might see one sun set only for the binary pair to rise on the opposite horizon, plunging the world not into darkness, but into a lurid crimson twilight that could last for weeks. This is not a place of rest. It is a world of eternal anxious light, a place where the concept of sleep might never have evolved. The very psychology of any being living here would be forged in this constant, unrelenting bath of radiation and complex light. The sky is not a predictable clockwork machine. It is a chaotic, beautiful and terrifying kaleidoscope, a constant reminder of the violent forces that govern this world's every moment. This celestial dance is more than just a visual spectacle. It is the engine of a climate so violent, so profoundly unstable, that it defies our terrestrial experience. The heat and energy bathing this planet are not delivered in a steady, reliable dose like the Earth receives from our Sun. Here, the energy budget is a story of catastrophic peaks and devastating troughs, dictated by the planet's looping, spiraling journey around its three stellar masters. As the planet swings inward on its elliptical path, drawing closer to the tight binary pair, the radiation influx skyrockets. The light from these two stars, one intensely hot and the other a cooler but larger giant, combines into a focused thermal lance. But the true terror begins when the planet's orbit synchronizes with the distant third star, creating those moments of trisolar conjunction. When all three suns are high in the sky, the planetary surface is subjected to an onslaught. It is a summer of unimaginable ferocity. Scientists modeling this environment speak of it in apocalyptic terms. Surface temperatures could spike by hundreds of degrees in a matter of mere days. Oceans, if they exist, would not just warm, they would flash boil at the equator, sending continent-sized plumes of superheated steam into an already turbulent atmosphere. This sudden massive injection of water vapour would generate hyper-hurricane storms so vast they could swallow entire Earth continents, with wind speeds exceeding the speed of sound. The planet would be caught in a runaway greenhouse effect, a temporary recurring vision of hell. Any nascent life clinging to the surface would need to find shelter deep underground or in the polar regions to survive this periodic planet-sterilizing blast furnace. Yet this inferno is not permanent. The same orbital mechanics that create the great heat also conspire to bring about an equally brutal cold. As the planet swings out on its long orbit, away from the central binary and into the shadow of the distant third sun, the energy it receives plummets. This is the Great Winter, and it arrives not with the gentle turning of seasons, but with the terrifying speed of a switch being thrown. Temperatures would crash. The superheated steam in the atmosphere would rapidly condense and freeze, falling not as gentle snow, but as a torrential globe-spanning blizzard of ice. The same oceans that were boiling just months before could flash freeze their surfaces, cracking into continent-sized plates of ice. Glaciers born in the upper atmosphere would descend upon the landscape, carving new valleys in a geological blink of an eye. The world would transform from a furnace to a cryochamber in a fraction of its year. This is a climate of extremes, a world locked in a permanent violent oscillation between fire and ice. There is no temperate zone, no gentle spring or mild autumn. There is only the furnace and the freezer. Any ecosystem here would have to be built on a foundation of incredible resilience, capable of hibernating through one extreme and estivating through another. The very geology of the world would be shaped by this thermal whiplash. Rocks would be subjected to immense thermal stress, expanding under the trisolar glare and contracting in the deep freeze, causing them to shatter and exfoliate over millions of years, creating vast deserts of sharp crystalline sand. The atmosphere itself would be in a constant state of flux, thickening and thinning its chemistry, radically altered by the boiling oceans and freezing skies. It's a world that is perpetually at war with itself, driven mad by the inconsistent affections of its three suns, and the light and heat are only the most obvious consequences of this cosmic arrangement. Beneath the surface, a far more powerful and insidious force is at work, shaping the very soul of the planet. For this world does not just orbit its suns, it is tortured by them. Every moment of its existence it is caught in a gravitational tug-of-war, a relentless battle for dominance fought between three stellar behemoths. On Earth we experience the gentle, predictable pull of our moon, and to a lesser extent our sun. This pull creates the tides, the rhythmic rise and fall of our oceans. It is a force we have harnessed, a pulse that life has adapted to for eons. Now multiply that force, complicate it, turn it from a simple rhythm into a discordant, chaotic symphony of gravitational stress. The planet is being pulled not by one, but by three separate and powerful gravitational sources, each moving relative to the others. This is the infamous three-body problem, made manifest not as a mathematical exercise in a world's physical reality. The planet's orbit is not a clean, simple ellipse. It cannot be. Computer simulations reveal a path that is a masterpiece of controlled chaos, a stable but non-repeating trajectory. It wobbles, it precesses, it stretches and contracts. From one year to the next, its path through space is never precisely the same. It is a drunken, staggering waltz through a gravitational minefield. This orbital instability has a profound effect on the planet itself. The tidal forces at play are astronomical. As the planet swings close to the binary pair, their combined gravity seizes it in a cosmic vice. The world is stretched, its spherical shape distorted into an ellipsoid. The very crust of the planet is being flexed. This is not just a tide of water, it is a tide of rock. Imagine mountains rising and falling by hundreds of feet with each orbital pass. Imagine tectonic plates grinding against each other, not from slow internal convection, but from the direct, irresistible pull of external stars. This planet would be a geological nightmare. The constant stretching and squeezing of its crust would generate immense friction and heat within its mantle. This heat must escape. The result would be volcanism on a scale that dwarfs anything in our solar system. Supervolcanoes, vast calderas hundreds of kilometers across would pepper the surface, perpetually erupting, spewing billions of tons of ash and sulfur into the tortured atmosphere. The entire planetary surface would be in a constant state of renewal and destruction, a landscape of fresh lava flows and crumbling tide-shattered mountain ranges. This gravitational torment would make establishing any kind of stability almost impossible. Earthquakes would not be isolated events. They would be a continuous shuddering reality, the planet's crust groaning under the strain. The world is literally being kneaded like dough, its interior superheated, its surface perpetually broken. It is a world on the rack, a body stretched and compressed by forces that should by all rights have torn it to pieces billions of years ago. Which brings us to the most profound mystery of all. We have seen the chaos. We have witnessed the violence of the climate and the fury of the gravitational tides. The single greatest question is not what this world is like, but why it is here at all. Why hasn't it been ripped apart? Why hasn't it been flung into one of its suns, or ejected into the cold darkness of interstellar space? How in this maelstrom of competing forces has this impossible planet managed to survive? The answer, it seems, lies not in brute strength, but in a delicate, almost miraculous feat of celestial choreography. The planet does not exist in a simple free-for-all system. It survives because the system is hierarchical. The two central stars, the white dwarf and the red giant, form a very tight, stable binary. They orbit each other, closely behaving from a great distance, almost as a single gravitational object. The third, more massive yellow sun orbits this central pair from a much, much greater distance. This separation is the key. It creates a zone of relative gravitational stability, a narrow habitable corridor in the midst of chaos. The planet exists within this corridor, orbiting the central binary pair in a careful synchronized dance. It is close enough to the binary to be captured by their dominant gravity, but far enough away that the perturbations from the distant third sun are not immediately fatal. This is a system of orbital resonance, a state of gravitational harmony that allows for long-term survival. Think of it like a set of celestial gears. The planet completes a specific number of orbits around the central binary. For every single orbit, the binary completes around the distant third star. This resonance prevents the gravitational nudges from the third star from accumulating. One nudge that might pull the planet outward is cancelled out by a later nudge that pushes it back inward. The planet is in essence a gravitational gyroscope, its complex orbit, a finely tuned mechanism that maintains its balance against the relentless external forces. It is a dance on a razor's edge. The simulations are breathtakingly precise. If the planet's orbit were just a few percent wider, the pull of the third sun would eventually grow dominant, and the planet would be ejected from the system. If it were a few percent closer, its orbit would decay, and it would spiral into one of the central stars. Its very existence is a testament to an incredible cosmic coincidence. This planet must have formed in this precise orbital configuration, or it must have migrated there through a process of unimaginable gentleness and precision. It has held this impossible orbit not for millennia but for billions of years. It has weathered the gravitational storm, survived the tidal stresses, and endured the climatic fury, all because it inhabits a sliver of gravitational calm so narrow it borders on the miraculous. We are looking at a survivor, a world that has walked the tightrope over an abyss of chaos for eons. It has pushed our understanding of how planetary systems form and evolve to the absolute breaking point. It demonstrates that even in the most violent and unpredictable corners of the universe, a kind of stability, a strange and precarious form of permanence can take hold. The planet has found a way to endure. The physics of its survival, while extraordinary, are now within our grasp. But this only deepens the mystery and leads us to a far more tantalizing question. We have explored the world of rock and gas, of light and gravity. We have seen the crucible. But what of life in this realm of perpetual twilight and searing heat, of global winters, and a constantly trembling surface? Could anything more than geology persist? In this place where the very definition of a day is meaningless, and the ground beneath your feet is never truly still, could the tenacious spark of biology find a foothold? The forces that shape this world are hostile beyond our darkest nightmares. And yet, the universe has surprised us before. Having survived the physics of its birth, we must now ask, could anything possibly survive the biology of its existence? And so the planet holds its course, a gravitational survivor, a ghost that has learned to dance between three fires without being consumed. We have charted its impossible path, a celestial tightrope act performed over an abyss of chaos, and proven that it can endure. But to simply exist is not the same as to live. We've unravelled the puzzle of how it stays in the sky, a triumph of mathematics and sheer cosmic luck. Now we must confront the question that has been burning beneath every calculation, the ultimate inquiry that drives our journey into the dark. Could anything or anyone actually call this bewildering world home before a single microbe could ever stir the planet itself? Would have had to perform a second miracle even more improbable than its orbital stability. It had to be born in the first place. A single infant star is a place of relative calm, its protoplanetary disk a spinning nursery where dust and gas can patiently coalesce over millions of years. But here, in a trinary system, that nursery is a war zone. The gravitational tides of three separate stars would have churned the primordial disk into a maelstrom, a tempest of competing forces tearing apart the very building blocks of planetary formation. Most of our simulations show such disks being shredded, their precious material either flung into the interstellar void or devoured by one of the parent suns. How then did this world ever assemble itself? The clues lie hidden inside our most powerful supercomputers machines that can compress 1 billion years of cosmic evolution into a single week. Inside these digital universes, we construct virtual trinary systems and watch them unfold. We see stellar winds clashing gravity-twisting space and dust clouds swirling like smoke. And within that simulated chaos, we are beginning to glimpse a few fantastical pathways to creation. Perhaps the planet didn't form where we see it now. It could have been born in the calmer outer reaches of the system, orbiting just one of the stars only to be violently kicked inward by a gravitational disturbance, a game of celestial billiards that miraculously left it in a stable, albeit terrifying, new orbit. Or maybe it was an orphan to begin with. A rogue planet born elsewhere and wandering the galaxy alone that was captured by the intricate gravitational net of this triple-star family. It's a breathtaking idea, a lonely traveller finding a permanent if perilous harbour. Another even more exotic theory suggests the protoplanetary disk itself was so massive, so uniquely dense, that it collapsed under its own gravity, forging planets in a rapid, violent burst, a process more akin to making a star than the slow, gentle accretion we see in our own solar system. We don't yet have the answer, but the mere existence of this world tells us that planet formation is more robust, more creative, and far stranger than we ever imagined. It is a testament to the universe's relentless drive to build complexity, even in the most hostile of settings. But assuming it formed a solid globe of rock and iron, it would immediately face a new unrelenting assault. To be a cradle for life, a world needs an atmosphere. It needs a blanket of gas to regulate temperature, to provide pressure for liquid water, and to shield the surface from the sterilizing energies of space. Yet an atmosphere here would be under a constant three-pronged attack. Each of the three suns unleashes a stellar wind, a torrent of charged particles streaming outwards at millions of kilometers per hour. A planet in this system isn't weathering a storm from one direction. It is caught in a cosmic crossfire. This tripartite hurricane of plasma would act like a celestial sandblaster, relentlessly scouring away any gas the young world could cling to. For an atmosphere to survive even a few million years, the planet would need a guardian. It would need a planetary magnetic field, a magnetosphere of immense power and endurance. Forged in the churning of a molten metallic core, this invisible shield would have to be robust enough to stand firm against the combined fury of three separate stellar tempests. We can almost picture it a shimmering teardrop-shaped bubble in space, deflecting not one, but three distinct streams of lethal particles, a cosmic battle of magnetism against radiation fought every single second. Without such a dynamo spinning at its heart, the planet would be stripped bare, left as a silent, airless rock forever exposed to the raw vacuum of space. Even if this magnetic shield held firm, the atmosphere it protected would be bathed in an extraordinary spectrum of light and radiation. Imagine a world illuminated by three different suns, perhaps a brilliant, massive blue star, a familiar yellow-white sun like our own, and a dim, brooding red dwarf. The sky would never be simply blue. It would be a constantly shifting canvas of blended colours, a world painted in three shades of light. But this light carries with it immense energy. The combined ultraviolet and X-ray radiation pouring down from three stars would be a profound challenge for the chemistry of life as we know it. On Earth, our ozone layer is a fragile shield against the UV rays of just one relatively placid star. An atmosphere here would need far more robust defences to prevent the surface from being sterilised. This intense radiation would drive atmospheric chemistry in completely novel directions. It could break apart molecules like water and carbon dioxide, leading to the escape of lighter elements like hydrogen, slowly bleeding the planet of its life-giving ingredients. Or it could catalyse the formation of complex organic molecules, creating a thick primordial smog, a planetary-scale chemical laboratory powered by three suns. The very air could become a thick orange haze, a rich soup of prebiotic compounds, but one that might block most visible light from ever reaching the surface below. The sky itself could become both a shield and a shroud, a paradox for life trying to gain a foothold. And then there is the heat. Our concept of a habitable zone, the gentle Goldilocks region, where water can remain liquid, is beautifully simple for a single star. It's a concentric ring, a predictable band of cosmic real estate. For a planet orbiting three suns, that concept shatters into bewildering complexity. The habitable zone is no longer a stable ring. It's a dynamic, pulsating, three-dimensional volume that warps and twists as the stars dance around each other. As our planet moves through its orbit, it would swing closer to one sun while moving away from the other two. The energy it receives would never be constant. It would flicker. This could create the most extreme seasons imaginable. Not the gentle, predictable, tilt-induced seasons of Earth, but a chaotic climate driven by the planet's proximity to its three variable furnaces. One period of its year might be a scorching inferno as two of the suns align in its sky, creating a double noon that could boil oceans. Another phase might see it cast in the dim, ruddy glow of the most distant star, plunging temperatures into a deep freeze. A day on this world would be a cascade of sunrises and sunsets, with shadows that lengthen and shrink, twist and multiply as the three light sources trace their complex arcs across the sky. For life to arise here, it would need to be incredibly resilient, capable of adapting to wild, unpredictable swings in temperature and light, perhaps by hibernating for millennia, or by thriving in the subterranean oceans far from the chaotic whims of the sky. These are the challenges formation in a gravitational blender, the survival of an atmosphere under a triple-barreled assault, and a climate of mind-bending extremes. For decades, these problems seemed so insurmountable that most astronomers simply wrote off trinary systems as sterile, beautiful but barren. The physics seemed too hostile, the odds too long. But we have entered a new era. We no longer have to rely on imagination and theory alone. We now have the tools to pull this world from the realm of abstraction and see it for what it truly is. We have the power to put these theories to the test. That power resides in a magnificent new eye on the cosmos, an instrument so sensitive it can decipher the chemical secrets of worlds light years away. The James Webb Space Telescope is not just another observatory. It is a time-travelling detective purpose-built for a cosmic interrogation. It doesn't look at these planets directly, they are far too small and dim next to their parent stars. Instead, JWST performs a kind of cosmic magic. It waits for that precise fleeting moment when the planet passes directly in front of one of its stars from our perspective. In that instant, a tiny fraction of the starlight shines through the planet's atmosphere on its way to Earth. That journey, though, only a few hundred kilometers through the planet's gaseous envelope, changes the light forever. It becomes a message in a bottle. As the starlight passes through the atmosphere, different molecules of gas will absorb very specific frequencies, very specific colors of infrared light. Carbon dioxide will steal one sliver of the spectrum, methane, another water vapor, yet another. When that starlight finally reaches JWST's mirrors after its journey across the interstellar void, it arrives with a barcode, a pattern of missing colors that tells us exactly what the planet's atmosphere is made of. This technique, known as transmission spectroscopy, transforms a distant pinprick of a world into a laboratory. We're no longer just guessing if it has an atmosphere. We're analysing its contents. For the first time, we're on the verge of knowing. Does this planet have the thick nitrogen-rich atmosphere of an Earth, or the crushing carbon dioxide-choked atmosphere of a Venus? Is it a water world with an atmosphere saturated with vapour, hinting at the presence of vast planet-girdling oceans below, or is there nothing? Is it a barren rock, its primordial air long since lost to the stellar winds, a confirmation of our most pessimistic theories? The data that JWST is collecting at this very moment holds these answers. Each photon it gathers is a clue, a piece of a puzzle billions of years in the making. And we are looking for more than just air. We are hunting for the telltale signs of life itself. We are searching for biosignatures. On Earth, the vast quantity of oxygen in our atmosphere is a profound anomaly. It's a highly reactive gas that shouldn't be here in such abundance. It's constantly being replenished by the planet's photosynthetic life. The simultaneous presence of oxygen and methane is another powerful sign, as these two gases should quickly destroy each other. Finding them together suggests two powerful biological engines are at work, one producing oxygen and one producing methane, in a state of chemical disequilibrium that points directly to a living, breathing biosphere. But would life on a planet with 3 suns produce the same signatures? To assume so is to fall prey to the most dangerous bias in science, a failure of imagination. This world challenges us to think beyond our singular experience. Perhaps life here evolved in a low-oxygen environment, protected from the intense radiation by a different set of atmospheric gases. Maybe its metabolism is based on a different chemistry producing waste gases that we have never even considered to be a sign of life. We must search for any chemical imbalance so glaring, so out of place, that it defies a purely geological explanation. We are looking for the planet's own unique chemical scream, its own biological fingerprint written in a language we're only now beginning to learn how to read. The search forces us to completely demolish our old comfortable definitions of a habitable world. The Goldilocks zone was a beautiful, simple idea, but it is an idea born of a single sun. It reflects our own cosmic provincialism. Perhaps habitability is not about calm, steady warmth. Perhaps for some forms of life it is about change. Perhaps life could evolve to harness the energy of 3 different types of starlight, its photosynthetic machinery tuned to a wider, more complex spectrum of light than anything on Earth. Perhaps the extreme seasons are not a bug, but a feature, a powerful driver of evolution that forges life of incredible toughness and adaptability. Life might not be on the surface at all. It could thrive deep underground, powered by geothermal energy from the planet's core, utterly indifferent to the celestial light show above. It could flourish in a global ocean sealed beneath a crust of ice, kilometers thick, a stable, dark, warm environment, completely decoupled from the climate chaos at the surface. The planet's 3 suns might be nothing more than a faint mythological legend to creatures that swim in an eternal watery darkness. The lesson this world teaches us is that the universe doesn't care about our expectations. It is not obligated to conform to the narrow sliver of reality we occupy. The conditions we consider just right might simply be our conditions, not a universal blueprint for biology. And so we stand at the climax of our quest. We have journeyed from the initial disbelieving detection of a world that shouldn't exist, through the dizzying physics of its survival, to the ultimate biological question. We have built the tools and sharpened our theories. Now we listen. The faint light from that distant tripartite system has travelled for centuries across the gulf of space. It has journeyed past nebulae and star clusters, a silent messenger carrying the secrets of a world with 3 suns. That light has now completed its journey. It has been captured by our mirrors focused onto our sensors and translated into data. Within those streams of numbers lies a story of chemistry, of climate, of radiation, and just maybe a story of life. The signals are on our screens, the story's waiting to be read. The only question left is, are we truly ready for the answer? And so, we are left here in the lingering afterglow of a triple sunset, a spectacle we once relegated to the realm of pure fantasy. We have journeyed across the unfathomable gulf of interstellar space, guided by the faintest of whispers in our data. We have navigated the turbulent currents of scientific skepticism and wrestled with the stubborn limitations of our own technology. All of it has led to this single, breathtaking truth, a world that ought not exist serenely tracing its path through a gravitational labyrinth woven by 3 suns. This is not merely the discovery of another planet. It is the moment the universe pulls back a curtain we never even knew was there, revealing a stage vast and wild, beyond all our prior conceptions. It is a profound and humbling punctuation mark at the end of a sentence we thought we had already finished writing. To stand at this precipice of understanding is to feel the solid ground of cosmic certainty crumble away, replaced not by an abyss of confusion, but by an infinite ocean of possibility. For decades, our understanding of planetary genesis was built upon a foundation of elegant, almost pastoral simplicity. We envisioned a lone star, a gravitational anchor around which a vast, orderly disk of dust and gas would spin. From this primordial platter, particles would cling to one another, growing from pebbles to boulders, from planetesimals to full-fledged worlds in a stately, predictable cosmic ballet. Our own solar system, with its relatively stable near-circular orbits, was the cherished template, the blueprint we projected onto the cosmos. We sought echoes of our own home, convinced that nature favours such quiet, stable nurseries. This planet, this impossible survivor, doesn't just challenge that blueprint, it sets the original parchment ablaze. In its existence lies the undeniable proof that our model of the universe was not wrong, but profoundly beautifully incomplete. We were children drawing a map of our own backyard, declaring it the entire world. The gravitational dynamics of a multi-star system are not a gentle ballet. They are a violent, chaotic maelstrom. Imagine the complex interplay, the relentless push and pull. 2 stars might orbit each other closely, a fiery pair of cosmic dancers, while a third, more distant companion circles the pair. This creates a gravitational field of dizzying complexity, a landscape of treacherous hills and deep, unstable valleys. Any fledgling planet forming within this system is not a favoured child in a calm nursery, but a tiny ship tossed on a ferocious sea. The gravitational tides are immense, capable of tearing a nascent world apart before it can even properly form. The orbital pathways are a minefield of chaotic zones and ejection vectors. By all the laws of celestial mechanics, we held dear any clump of matter large enough to be called a planet should have been unceremoniously flung out of the system, a lost orphan condemned to wander the frozen dark between the stars. Yet this world endures. It survives. Its continued presence forces us to confront a far more intricate and perhaps more violent reality of creation. It suggests that planetary formation can occur under conditions we previously deemed untenable, in the frantic high-energy heart of a gravitational storm, how the answers are still coalescing, emerging from the frantic scribbles on 1,000 whiteboards. Perhaps the planet formed far out in the system's calmer frontiers, and was then shepherded inward through an impossibly delicate sequence of gravitational nudges. This would be a migration of such exquisite precision, it borders on the miraculous, a cosmic thread-the-needle maneuver on a scale of millions of kilometers. Or maybe, in a more radical departure from our theories, the planet formed with breathtaking speed, coalescing from the primordial disk so rapidly that it achieved a stable mass and locked into a rare island of orbital stability before the system's chaotic dynamics could tear it asunder. These aren't just minor adjustments to our theories, they are foundational aftershocks that demand a complete architectural review of our cosmic models. We are now compelled to consider that the universe may have multiple, dramatically different pathways to building worlds. The calm, stately process we observe around single stars like our own might just be one of many recipes. There may be another, a frantic and violent method, one that unfolds in the heart of gravitational chaos, forging planets in fire and fury. These worlds, the survivors of such a brutal upbringing, would be fundamentally different. They are not the products of gentle accretion, but the victors of a cosmic demolition derby, a testament to resilience on a planetary scale. Every multi-star system we once dismissed as too chaotic, too hostile for planet formation, has now been restamped with a giant tantalizing question mark. We have been looking for life in the quiet suburbs of the galaxy when all along it might also be thriving in the heart of the bustling, chaotic metropolis. This realization sends a powerful ripple through the most profound question we have ever asked: are we alone? For so long our search for extraterrestrial life has been anchored to the concept of the Goldilocks zone, that narrow temperate band around a single star where liquid water might exist. We sought cosmic twins of Earth, orbiting cosmic twins of our Sun. It was a search defined by familiarity, a quest for a mirror of ourselves. This planet with its 3 suns shatters that mirror. It forces us to redefine what a habitable world could even be. The very idea of a stable Goldilocks zone becomes almost meaningless here. An orbit that brings the planet close to the fiery central pair could create blistering runaway greenhouse conditions. As it swings farther out toward the distant 3rd star, it could be plunged into a deep, lasting freeze. Yet life is tenacious. Life is adaptable. Could an ecosystem evolve not with the gentle, predictable rhythm of 4 seasons, but with a complex, chaotic dance of 3 distinct stellar cycles? Imagine a world where the sky is never truly dark, where a perpetual twilight is illuminated by the distant glow of at least one sun. Imagine plants that have evolved to photosynthesize 3 different colors of light, perhaps changing their very biochemistry as they track the dominant star in the sky. Perhaps life doesn't cling to the surface but thrives in the depths of a global ocean, shielded from the erratic blasts of stellar radiation by a thick mantle of water or ice, its metabolism powered by hydrothermal vents, drawing energy from the planet's gravitationally stressed core. On a world like this, the very definition of a day or a year would be a fluid shifting concept. Survival would demand an unprecedented level of biological adaptability. Could intelligent life arise in such an environment? What kind of science, what kind of philosophy, what kind of art would emerge under a sky dominated by a celestial waltz of 3 suns? Their astronomers wouldn't have discovered the simple elegance of Kepler's laws, but would have been born into a reality of mind-bendingly complex orbital mechanics. Their sense of time, of stability, of cosmic order would be fundamentally alien to our own. Perhaps they would be a species that values adaptability above all else, their entire culture shaped by the need to survive radical, unpredictable shifts in energy and light. The discovery of this planet doesn't give us answers, but it radically expands the vocabulary of the question itself. It tells us that the conditions for life might not be a narrow set of prescriptive rules, but a vast and diverse spectrum of possibilities, many of which we are not yet creative enough to even imagine. The number of potential homes for life in our galaxy has not just increased, it may have multiplied by an order of magnitude, and so we look to the future not with the quiet confidence of those who have found an answer, but with the burning electrified curiosity of those who have just discovered an entirely new kind of question. The discovery of this one world is a clarion call to astronomers everywhere. It is a cosmic treasure map pointing not to an X that marks the spot, but to the countless other multi-star systems we had previously overlooked. With a new generation of telescopes now coming online, instruments of breathtaking power and sensitivity, we are poised to conduct a new survey of the sky. We will no longer filter out the complex light curves of binary and trinary star systems. Instead, we will target them. We will stare into their chaotic hearts, hunting for the telltale dimming of a planet crossing its suns, or the subtle gravitational wobble that betrays a hidden world. Each new discovery of this kind will be another crucial data point, another piece of the puzzle. Are these impossible worlds exceptionally rare, the 1 in a billion survivors of a gravitational lottery? Or are they shockingly common, a standard feature of galactic architecture that we were simply blind to? Finding more will allow us to test our newly forming theories. We can analyze their atmospheres, searching for the chemical fingerprints of biological processes. We can map their orbits with ever greater precision, understanding the delicate balance that allows them to survive. We are standing at the dawn of a new era in exoplanetary science, moving beyond the simple search for Earth-like planets and embracing a hunt for the truly exotic, the truly alien. We are becoming connoisseurs of cosmic impossibility, actively seeking out the worlds that our old theories swore could never be. It is a thrilling, humbling, and revolutionary shift in perspective. This journey from a flickering anomaly in our data to the confirmation of a world orbiting 3 suns is more than a scientific achievement. It is a story about us. It reflects our own relentless, unyielding drive to look past the horizon, to question the received wisdom, and to embrace the mysteries that lie in the dark. Every time we point a telescope toward the sky, we are holding up a mirror to our own cosmic insignificance, and simultaneously to our profound ability to comprehend the universe that dwarfs us. We are a species defined by our curiosity, a transient arrangement of stardust that has evolved the capacity to look back at the stars and understand its own origins. This world with its triple suns is a powerful reminder that the universe has no obligation to conform to our expectations. It is not bound by the limits of our imagination. Its creativity, its diversity, its capacity for generating sheer, unadulterated wonder will always outpace our ability to predict it. We once thought the Earth was the centre of everything, a belief shattered by a simple telescope. We once thought our galaxy was the only one, a notion dispelled by the discovery of endless island universes. Now the idea of a normal solar system has been irrevocably broadened. Each of these revelations was not an ending, but a new beginning, an invitation to ask bigger, bolder questions. And so we leave you with the image of that alien sky. A sky where a brilliant yellow sun might be joined by a fiery red dwarf, while a distant blue-white giant paints the landscape in ethereal hues. It is a place of breathtaking beauty and terrifying chaos, a world that embodies the intricate and often paradoxical nature of the cosmos itself. Its existence is a gift, a piece of knowledge that enriches us all, a humbling lesson that no matter how much we learn, the universe will always have another secret, another wonder, another impossible world waiting just beyond the edge of our understanding, ready to change everything we thought we knew. The story of the cosmos is not a book to be read, but a library of infinite volumes, and we have only just learned how to open the first page.